So I think I can finally have the ability to introduce Lev to present his second lecture of his mini course series. And so I apologize for the delay one more time. And so here's the continuation of the mini course.
Okay, thank you, Andrei. So let me begin by quickly reminding the story about matrix factorizations that we were discussing last week. So the category is comes from a fine variety and a function over the variety, and the category is interesting here because it describes category of morphisms between two Lagrangian subvarieties of cotangent bundle to X, namely the zero section and the graph of dW. So there is a two category of cotangent bundle, and there are two objects which intersect in a bad way, perhaps, if critical points of W are degenerate. If W is not quadratic in the vicinity of its critical points, if it's of higher degree, then the category of matrix factorizations describes properly what is the morphisms between these two badly intersecting Lagrangians. So an object, so category of matrix factorizations is a deformation of the category of coherent sheaves by this superpotential W, and our description matches the description of a derived category of coherent sheaves or derived category of modules in terms of homotopy category of complexes of free modules. So for matrix factorizations, we have a Z mod 2 graded module and a so-called twisted differential which squares to W times identity. And morphisms between two matrix factorizations are defined as morphisms between the modules, Z mod 2 graded modules over C of X, with a differential, which is a commutator with twisted differential. And this commutator differential squares to 0. So this is a standard homotopy story, how you build a DG category out of complexes of modules. There is a notion of dual matrix factorization. For a given matrix factorization, its dual is a factorization of the opposite superpotential, negative W, and there is a slight change of sign in twisted differential so that it will square to negative W. One can also tensor multiply two matrix factorizations over the same variety, and you tensor multiply the modules and add the twisted differentials. As a result, the square will be the sum of superpotentials, because d1 plus d2 squared is d1 squared plus d2 squared plus anti-commutator between them, which is 0. So the squares add up, the superpotentials add up. This is an important technical feature. Also here, let me insert a comment that maybe I should have said that before. I'm sorry. Now I have slight technical difficulty with my pen. Misbehaves today. Sorry. So let me make a comment that Mikhail Kavanov and I used category of matrix factorizations previously in order to categorify SUN Homfley polynomial of links. So matrix factorizations have already appeared in the story about categorification of link invariants, and eventually I hope to explain what might be the relation with what happens here. So this story is a bit different but related. So among all matrix factorizations, the simplest ones technically are so-called Kazul matrix factorizations. If your superpotential is the product of two polynomials, then it's very easy to arrange a matrix factorization between two rank 1 modules, shooting by P and Q back and forth. As you see, the differential indeed squares to PQ both ways. And more generally, if W is a sum of products, then you can arrange for a Kazul matrix factorization of these two lists of polynomials, which would be tensor product of matrix factorizations of individual pairs. It is convenient to represent these many polynomials P and Q as columns. In each row, you have a pair. So there are so-called row operations which you can perform on polynomials P and Q, which change matrix factorization up to isomorphism. You do not even need homotopy. So you can add P1 to P2 with some coefficient and subtract Q2 from Q1 with the same coefficient. Or you can add P1 to Q2 because here they are presented. So this is a very convenient technical trick. And based on row operations, you can prove an easy theorem that if polynomials P form a regular sequence, then polynomials P and W determine the Kazul matrix factorization. The choice of Q different choices of Q can be related through row operations. So it doesn't matter. So the main technical trick of constructing important matrix factorizations, whenever you face a superpotential and you know that it must have a canonical matrix factorization, something special. The trick is to use Bezout theorem plus Kazul complex. So you look at your superpotential and use Bezout arguments to present W as a sum of products, meaning you see that W belongs to ideal generated by polynomials P. And you find suitable Qs and write the Kazul matrix factorization. So the first example of this construction is identity by module matrix factorization. So generally, if you consider matrix factorizations over x1 cross x2, with the superpotential being the difference of superpotentials, one from x1 and one from x2, then it determines a functor from matrix factorizations of W1 to matrix factorizations of W2 by tensoring with this matrix factorization M. Sorry, still have that. So I'm sorry. So here is this matrix factorization, which defines a functor. So what would be identity by module for matrix factorization, which depends on single variable, it's just C and W of X. So you have to come up with a canonical matrix factorization of W of Y minus W of X. And obvious choice is factor out Y minus X, and the other factor will be divided difference. W, I abbreviated to WXY. And so this Kazul matrix factorization in red box gives you identity functor. Then you can immediately compute Hochschild homology, cohomology of the category of matrix factorizations, let's say of one variable, as the space of endomorphisms between identity of identity functor. So in other words, in the category of matrix factorizations depending on x and y, you take tensor product of this identity one with its dual and take homology. Same as take home from M1 to M identity to M identity, you just tensor it with dual. So you get Cazul matrix factorization here. This one. And now you use row operation to, I'm sorry, I'm showing you what is under the hood. So you get rid of y minus x, and then you see that divided difference is simply derivative of w plus terms proportional to y minus x. So you can kill those again by row operation. And you end up with a complex y minus, with a complex w prime 0, Cazul complex. So you end up with what's called Jacobi algebra of singularity of w, quotient of c of x by w prime. So that's the whole.
Sorry, Lev, is y here a one-dimensional thing, or is it y and x are?
Well, yes. So I consider a single variable. So I consider c with coordinate x and c with coordinate y.
Okay. And what would be the case? What would be the analog if I had if it's you can ask the same question if I have a superpotential of a number of variables? What would that look like?
Yes. Then you have to do it for all pairs of matching variables, and in the end, you would have a Cazul complex which kills all partial derivatives of w. So you kill all derivatives of w in a derived way. So you would have a Cazul complex with, let me say, some theta I dw dxi. That will be your differential over c of x's and thetas.
And what would be this identity bimodule? What would it look like?
Now you have many choices. So in the left column, you would put x1 minus y1, xn minus yn. And it doesn't matter what you choose for the right column. You know that w of y's minus w of x's belongs to the ideal generated by differences. So you can present it as a sum of xi minus yi times something I. And then you put those somethings in the right column, and it doesn't matter. And then you compute, if you want Hochschild cohomology, you tensor multiply this matrix factorization by its dual, do some row operations, and end up with the Cazul complex, which kills partial derivatives of w. Does it make sense?
Yes, thank you. Thank you.
So generally, if w, if partial derivatives of w do not form regular sequence, then you would have interesting Hochschild cohomology. You'll have a derived Jacobi algebra, so to say. Okay, so now let me go back to where we finished last time. So we go back to important properties of matrix factorizations. So we mentioned last time so-called Knorr periodicity. If you multiply your variety by C2 with coordinates xy and add xy to the superpotential, then the category remains equivalent to itself, doesn't change. And the way to identify old matrix factorizations with new ones is to tensor them with the Koszul matrix factorization of x and y. Maybe here I should say there is a, there is a, I think I start having technical difficulties. There is a theorem, I think it was proved by Telemann, but okay, let me put it parenthetically that if critical locus of W is non-degenerate, meaning quadratic form of W is non-degenerate in directions transverse to the critical locus, then again, I do not formulate it properly, but it would be sufficient for now, maybe. Then matrix factorizations of W is equivalent to two periodic coherent sheaves on critical locus. This is not exactly correct. There is one slight correction, but let's ignore it for now. So matrix factorizations are really interesting when critical locus has singularities and W does not behave well in transverse directions. So in case of adding variables x and y, this is good, at least for variables x and y. You see non-degenerate quadratic form. So that's why adding x times y as a particular case of this theorem doesn't change your category. You just get coherent sheaves over point, which is critical locus of xy. Let me go back to Koszul duality. So there is a story that modules over a boson over an even variable A, derived category of modules over even variable K, is equivalent to derived category of modules over odd variable theta. So variable A has homological degree 2. This CT star is an extra action of C star, which provides homological degree to variables. So variables carry homological degree in this case, not just so homological degree is not just determined by your place in chain complex, but also variables carry it. So degree of A is 2, degree of theta is -1, and free module on one side corresponds to simple module on the other side. This is a well-known story. The equivalence between these two categories is can be described by a bimodule of A and theta equipped with a differential. So it's a differential bimodule. If you forget about one of the variables, A or theta, in this bimodule, then you see a resolution of a simple module in the other variable. So that's why it turns free into simple and back, basically. So the horror movie that I mentioned last time at the end is what would happen to this Koszul duality if you perturb these two equivalent categories by the same perturbation. So the categories are equivalent, so they share the same Hochschild cohomology, which parameterizes at least infinitesimally the deformations of the categories. So try to deform and Hochschild cohomology of both categories is C of A and theta. So from the A point of view, from the C of A module's point of view, well, A is your coordinate and theta is polyvector field. Actually, here we have only vector field since we have only one variable. From theta point of view, theta is coordinate and A is something weird, something really weird. So if you perturb by power of A, which is a good even Hochschild cohomology, so can be used for perturbation if you sacrifice Z grading, homological Z grading, then on the C of A side, you get matrix factorizations of A to the n. And this is manageable, and we discussed it last time. But on the theta side, on the odd side, which is preferred by derived algebraic geometry people, you will get an A-type, A-infinity type deformation. You get a multi-multiplication, so to say. It's a funny deformation of the category that you get on the C of theta side. So both are equivalent, but odd side requires a rather advanced description. Now the nice story about this equivalence, which we will see in application, is if we add an extra variety x on both sides of equivalence. So now we have x with A and x with theta. And on the A side, we add a superpotential A times W. So you have a variety x with superpotential with function W on it. You multiply it by A and say this is the superpotential. So then Cazul duality turns the superpotential into a differential on the theta side. So on the theta side, you get a DG scheme. So on the A side, you get matrix factorizations. On the theta side, you get a DG algebra, or you may say DG scheme, which kills with differential, which is designed to kill W. So if you have just single variable A, then this differential means that you take a quotient by W. So you're considering derived category of C of X mod W modules. Not the singular part of it, the whole category. And this equivalence at this perturbed level is described by a bimodule type matrix factorization. So now we have C of X and C of A theta. And in addition to the old differential, which was A theta, we now add a new differential, which is W dd theta. So the square of this d will be A times W. And you can use it to go from one side to the other, back and forth. So this is a differential bimodule with twisted differential. So you can tensor multiply matrix factorizations by it. You will get differential modules, or you can tensor multiply differential modules and get matrix factorizations. So you can check that D is really twisted. When you square, theta and dd theta do not anti-commute. They have anti-commutator equal to 1. And this is what produces A times W, because theta and dd theta do not commute. In the multiple variables case, so if you have many A's, then you can multiply each A by its own W. And on the right hand, you have a more complicated differential. And now there is no guarantee that you can remove thetas and just take a quotient, perhaps only when W's form regular sequence. So generally, a linear superpotential on the matrix factorization side will become, by Cazul duality, a true DG scheme with an important differential. So it will be derived, sort of derived algebraic geometry as you might have expected. So in our case, in our application, again, I'll talk about it in details later, we will consider a category of matrix factorizations with equivariance with respect to two Borel subgroups of GLN. Again, I will slide I will go very quickly over it because I will talk about it in details later, just to illustrate. So your variety X is Borel subalgebra, nilpotent radical, and the group GLN. And the superpotential you see is X times conjugation of Y. The group element parameterizes relative position of two flags. So you have standard flag and another flag parameterized by G, and there are two matrices XY. So now, by the trick that I just mentioned, you can trade either X, so superpotential is linear both in X and Y. So you can trade one of them for odd variables and turn superpotential into differential. So you can trade X for odd variables, and then you will get a derived Steinberg variety. Then you will get an essential differential. Or you can trade Y for odd variables, and then you will get Grothendieck Steinberg, which doesn't have to be derived, because in that case, conditions are regular. So this Kazul turns this matrix factorizations category into something more familiar to geometry representation theory people, which is variations of Steinberg variety. Finally, to finish with matrix factorizations, sometimes we need to pull them back. That's very easy. If you have a morphism from Y to X, you just and you have a polynomial of X, you pull it back to Y, and you can pull the whole category in the most obvious way back to matrix factorizations of Y. That's not a problem. With push forward, it is a problem because you have to do it in a nice derived way. So I don't want to go into all the details of push forward, just one example that we will use shortly. Suppose you have X and now you add an extra variety Z. So you have a projection which forgets Z. Now on X you have superpotential, you pull it back to X cross Z. And now you can push matrix factorizations along Z just by forgetting Z variable and hoping that you will not get infinite rank. So you have to just keep in mind that there is a danger of getting infinite rank when you do push forward. Another example, if you have a subvariety in X described by some polynomials being equal to 0, then you can push modules over this sheaves over this subvariety to matrix factorizations over the whole X of a superpotential which was 0 on your subvariety. So W belonged to ideal generated by polynomials P. So it could be presented as P dot Q. And then the push forward will be essentially tensoring with Kazul matrix factorization. Again, the choice of Q is not important. It's good. It helps. So Kazul matrix factorization is an example of pushing forward something from polynomials P being 0 to the whole variety X. So this is all we need to know about matrix factorizations. So the main lesson is Knorr, and that you can turn linear superpotentials into differentials.
Question. So when you say forget Z, do you mean you take, we push forward sheaves, or your matrix factorization was some?
You have three modules. Yes, we
don't take hierarchy homology that push forward, or we just
you have to do some contraction. Otherwise, otherwise you will get infinite rank. So you have to say something to make sure that you do not get infinite rank. For example, there could be some group equivariance in the background. So you will take, say, 0 weight with respect to something. So yes, the way it's written, there is a danger that you will get infinite rank, or the differential in the resulting matrix factorization will kill most part of C of Z. So something should happen to make sure that you don't get infinite rank by simply. I mean, but again, by forgetting Z, I mean you forget the structure of Z module, of C of Z module. Of course, all the powers of Z remain the same.
Right, but we don't take hierarchy homology. We just take just the push forward of a sheaf, or
yes, we hope to deal with affine varieties.
okay.
So if let me make a comment. So generally, apparently, matrix factorizations make sense on other varieties, not necessarily affine. But there is a catch. I will explain it in a very pedestrian way, which corresponds to my level of understanding. So when you deal with coherent sheaves over varieties, then you can simply work with complexes of vector bundles. And the differentials are just usual section from one bundle to another. In general, you could have other extension X from one vector bundle to another and form cones out of those. But there is apparently a theorem, people who know algebraic geometry know this theorem, that you can equivalently describe the same complex in terms of vector bundles with usual homes between them. So you do not need X to describe objects. You can get rid of them by changing your vector bundles. Now, in case of matrix factorizations, this argument wouldn't work because you can simplify one of the arrows. The arrow which goes, say, from left to right. You can so matrix factorization will be two vector bundles and differentials going both ways with the condition that they square to multiplication by W. Both differentials could be extensions, generally speaking. So you have to be careful with this homological algebra. So now if you straighten one extension, turn it into ordinary morphism, then the other one will get worse. So it's a complicated story. We work with affine varieties, but with equivariance with respect to some bad groups, such as Borel subgroups. So again, we have to be careful how we do certain operations. We have to use Chevalier-Eilenberg resolution from time to time. So there are some technical difficulties in working with matrix factorizations, which I still think would be simpler than doing similar things on the DG scheme side, or at least not worse than working on DG scheme side. Okay, so now let me talk about the two category of cotangent bundle. So I already mentioned it, so I could go faster maybe a little. So this is a combination of classical mechanics and algebraic geometry, or symplectic geometry and algebraic geometry. So the simplest objects in the in this two category of cotangent bundle are functions on X, and geometrically, so the category itself will be formulated in terms of X, but there is a geometric counterpart to this construction. So the things that we do by working with modules over C of X can be explained, at least intuitively, in terms of geometry of the cotangent bundle. So the object is a function over X, but geometry means Lagrangian subvariety, which is the graph of dW in the cotangent bundle. So the category of morphisms between two such objects, as I've said many times, is matrix factorizations of the difference between superpotentials. Why? What is the geometric counterpart of this definition? So there is a projection of cotangent bundle to the base. And under this projection, the intersection between the graphs of DWs, between these Lagrangian subvarieties, will project bijectively to the critical locus of W2 minus W1. Now, as I mentioned, the matrix category of W2 minus W1 lives in the formal neighborhood of critical locus, and in fact, it is coherent sheaves over critical locus if critical locus is sufficiently good, if it's smooth and quadratic form is non-degenerate in transfer. But the Taylor series is non-degenerate in transverse directions, the quadratic part of Taylor series. So therefore, indeed, if Lagrangian subvarieties intersect nicely, which means that critical locus has this property, then again, up to details of homological grading, you get coherent sheaves over their intersection in the form of matrix factorizations of this difference, because their intersection is exactly the critical locus set theoretically. And again, if critical locus is smooth non-degenerate, then it's exactly coherent sheaves. Now, the composition of morphisms is tensor product of categories is tensor product of matrix factorizations. And here, the fact that superpotentials add up plays crucial role. So when you go from 1 to 2, it's the first difference. From 2 to 3, it's the second difference. You tensor multiply them, and differences add up. You get the difference between 3 and 1. So this is very good.
I'm sorry to be annoying on this point, but suppose your Lagrangian is some singular Lagrangian, and I ask for homes from Lagrangian to itself. So what would it look like?
Sorry. So first of all, these Lagrangians are nice because they're just graphs of DW. Home between Lagrangian and itself will be matrix factorization of 0 superpotential over X. So essentially, it will be coherent sheaves over X. Essentially,
if X is smooth, right?
Yeah, and I will. I assume that X again. I'm not very precise here. So in my mind, my X is either a vector space or vector space minus something.
No, I'm just being a slightly annoying at the fact that this is. I don't think this is defined for a single Lagrangian. So for sometimes it's defined, sometimes it isn't. So I don't think you can represent any pair of single Lagrangian as graphs of something. Like for example, if I take one single Lagrangian and I want a home from itself, and I'm not sure how exactly to apply this.
You will see first examples shortly, and don't worry. I mean, this is our main example is a fibration over a singular Lagrangian, and that Lagrangian is a particular case of your envelope. So I will happily dwell on it as long as you wish. And
yeah, but envelopes are very special Lagrangians. They're very nice Lagrangians, like they're quantizable and stuff.
Yes.
And the general Lagrangian is not nice. So it's Okay. Anyway, I'm just. I was just curious.
I will give you. So if you want a singular Lagrangian, then you have to include auxiliary variables, and I will do it in a few minutes.
I don't think you can do it for general Lagrangians either. So for some of them you can, but I don't think you can like for example, take a curve in a plane.
Mm-hmm.
I'm not sure you can always parameterize a curve in a plane with the auxiliary variables.
To be honest, I do not know. I don't know that either. So it's an interesting question. But I will give you really.
But I know you're going to work with some specific ones which do have this presentation. So it's
but
this much I understood.
But the point of this description is that this is a definition. So if you cannot, So I hope that you can describe any Lagrangian subvariety by, say, introducing auxiliary variables if you have to. So if there is some Lagrangian subvarieties which cannot be described in this way, then I don't know. It would be very interesting to study this. But so far, this would be just definition. So look, on the geometry side, Lagrangians which can be presented in this way. And I will give you pretty bad ones. They will not even be Lagrangian in some bad situations. But at least, but it makes sense in terms of these definitions. But please keep bugging me. So it helps me if you challenge these statements. Thank you. So a general object would be an auxiliary variety and a superpotential which depends on coordinates of z and x. And the geometry, so in classical mechanics textbooks, it's called generating function depending on extra parameters or auxiliary parameters. Geometrically, you can visualize it the following way. So W determines a Lagrangian subvariety, the graph of dW determines Lagrangian subvariety in the product of cotangent bundles, or cotangent bundle to the product. And it is interpreted as Lagrangian correspondence, which is to be applied to the zero section of cotangent bundle of Z. So this means that you take preimage of a cotangent bundle of Z inside the product of cotangent bundles, and you intersect it with this Lagrangian W. So in the product of cotangent bundles, you have two conditions. That you have zero momenta corresponding to Z, and you sit on your Lagrangian submanifold determined by W. And then you project it onto X. Onto T star of X. So in a pedestrian description, if your W depends on X, so let's say one variable and one auxiliary parameter A, then this fibration LW is described by two equations. The conjugate moment is partial derivative of W, and partial derivative with respect to A must be 0. So this generally describes a Lagrangian subvariety in T star X, but there may be some pieces hanging over it because this dWdA equals 0 doesn't give you a one-to-one correspondence between what is upstairs and what is in T star X. So it gives you a fibration. So the most important example of this construction is when you want to describe a Lagrangian subvariety in C2, which is X equals to 0, just the P-axis. And then you need one extra variable A and superpotential A times X. Now, if you want bad examples, sorry. So here, let's say you want bad. Consider W of AX, oh, sorry. Consider W of A and X, which is, well, try AX squared and try A squared X, just as examples. So one of them will give you a cross, which is not exactly a cross in P and X. So these will be pretty good, pretty bad. And in usual geometry, if you try these, then people will tell you perturb them a little bit and you will get something nice. But again, in algebraic geometry, you're not supposed to perturb things. So you have to work with these W's. In terms of matrix factorizations, nothing bad happens. So these are seem still to be good objects. So for example, the first one will tell you that y equals 2ax and x squared is equal to 0, which is not bad. The second one will tell you that ax is 0. Let's say this one. Ax is 0 and y or p is equal to a squared. Which implies that y times x is 0, but it's not exactly y times x is 0 because it is in a sense square root of y times x is 0. So it's something weird. Is it singular enough, or you want more singular?
I think the variety, so your generating functions are like smooth Lagrangian correspondence with a smooth Lagrangian. And I think a general Lagrangian does not have that structure. Like a general Lagrangian is not quantizable, for example. Anything that has a smooth correspondence with a smooth variety can quantize, for example. A general Lagrangian you won't be able to quantize.
Okay, let me, this is an interesting question.
Even it's unknown to me whether you can put a general variety at least with something which has at least some kind of mild singularities. Like, is there what sort of Lagrangian resolution of singularity exists? Like, find a smooth Lagrangian correspondence with something which reasonably mild singularity. So that such theorem is unknown to me. So.
Okay, so these are my first examples, but look, regarding quantization, I do not. Okay, let me, if I may put this
like for example, if I take a stable envelope, it's a very nice Lagrangian. Although it may be like a stable envelope may have different irreducible components, but altogether it's a nice Lagrangian, has a nice correspondence with something nice. But if you put like individually reducible pieces in the stable envelope, those I don't think like you can put, take one individual piece, and I'm not sure those could be those as nice. Like even so that's where I would look for, even in the world of stable envelopes. I think if you look at the like I said, pick some reducible component in the stable envelope, then I'm not sure this can be like
I think it. Okay, let me put this off a little bit till we get to our examples, and then we could discuss it more specifically. As far as I understand, so let's take example of cotangent bundle to P1. It may appear from different quivers. So depending on which quiver you use, and so which symplectic description you use for this symplectic variety, sometimes your envelopes come natural, and sometimes components come naturally. So I do not quite understand all the details, but again, depending on how you describe T star P1, you may get components or the envelope, which would be zero section and cotangent space at North Pole, for example.
I think this somehow the most canonical example of a bad Lagrangian. If I look at so this is somehow beyond my expertise, but maybe other people listening in the seminar would know more. Like for example, if I take a characteristic cycle of an irreducible representation of even GLN, this is sometimes reducible, starting with like GL7 or GL8, and that means.
I'm sorry, you said characteristic what?
So for every representation GLN, it's some some D module, so you can ask its characteristic cycle, and that's generally speaking reducible, starting with like GL7 or GL8. I forgot the famous example by Kashevara, and so which means something kind of funny happens with those Lagrangians, with like individual components of that reducible thing. So I think that's a.
Okay, let me.
Anyway, some other people probably know more. This is like a classical geometric representation theory, so something. Well, anyway, I don't want to delay you anymore.
Thank you. So I will keep that in mind, and maybe when we get closer to the examples. So let me say that, so for these general objects, the category of morphisms would be take X with both auxiliary varieties and matrix factorizations of the difference of pulled back superpotentials. And composition of morphisms, when you deal with auxiliary variables, will be pullbacks and then push forward, the most standard thing that you could guess. And again, you hope that you do not acquire infinite rank or some technical properties, problems in doing push forwards. One way, for example, to avoid technical problems is when you have extra C star equivariance and say Z2 along which you push forward the intermediate auxiliary variables that you're supposed to forget when you compose matrix factorizations. Suppose that they have grading coming from C star action. So although you have infinite rank, but in each degree it's still finite. So that would be, that would save you from technical troubles. Now, what would be functors between these two categories? So functor, so one way to describe a functor would be to take an object in the product of cotangent bundles, just switch, in other words, Lagrangian correspondences between x1, between T star x1 and T star x2. So you would need a Lagrangian object in the product of cotangent bundles. I put bar over x1, meaning that you have to switch the sign of its symplectic form for this to work. So your functor will be auxiliary variables, which you might want, and the superpotential, which depends on them and on x1 and on x2. So generating function for symplectomorphism, symplectic map depends on old coordinates, new coordinates, and auxiliary variables. Again, this is very common in classical mechanics. So then the corresponding functor, so this data gives you an object in the category corresponding to T star x1 cross T star x2. So how would it act on an object in the category of x1, this functor? So you will get a matrix factorization. You will get a new object. So again, this is just classical mechanics. So you had auxiliary variables z1 of your object, auxiliary variables of the correspondence, and x1 also becomes auxiliary, and you take the sum of superpotentials of the object and of the correspondence. So you have many auxiliary variables. Your object initially had auxiliary variables z1, and then you add auxiliary variables of the correspondence, and also whole x1 from which you want to go also becomes auxiliary. And also you hope that Knorr periodicity will help you to get rid of so many auxiliary variables. In fact, this is what happens. Okay. So if you want to define a functor between two categories, you have to also explain how it acts on morphisms. So this is a quick illustration. Again, look under the hood, how Bezout and Kazul tell you how to construct action on morphisms. So suppose you have two simple objects in the category of x1. That's W1 of x and W2 of x. And the category of Holmes is this matrix factorization in green. Now the final objects, you have to add W1, 2 to both. And keep in mind that x So you go from variable x to variable y, and let's assume that our correspondence doesn't have auxiliary variables. Again, for simplicity, it's just described by function w12 of x and y. No auxiliary variables there. So keep in mind that when you add superpotentials in these formulas, here, then x becomes auxiliary variable. So in new objects, you have to give it different names for w1 tilde and w2 tilde, because now it's auxiliary, so it's different for every object. Only the base variety gives you common variables. So your home between the images of the objects is this matrix factorization category. So you start from this one, and you have to arrive at the second one. So you need a matrix factorization over all the variables. Here I cut the corners a little bit. You see that I use the same variable x in the initial and in the final. This will just simplify formulas slightly. So you have to find a canonical matrix factorization of the difference of these superpotentials. And luckily, you see that this difference of tilde ones minus difference of original ones becomes 0 when x equals x tilde. So Bezout tells you that you can factor it out, and then you get Kazoo complex. So by tensor multiplying by this k, you go from the first matrix factorization to this category of matrix factorizations to the second category. So in particular, suppose you're here I consider a case when just a moment. Why did I say? Okay, please ignore the open subvariety statement. Actually, it's correct, but I don't know why I put it in there. So let's ignore the open sub, because I didn't explain what to do with open subvarieties. Sorry. So this is a little bit out of order, this part. So just T star Cn. What would be identity functor from the category of T star of Cn to itself? So it's very easy to guess. In fact, again, comes from classical mechanics. You need n auxiliary variables, let's call them z, and you take a sum zi times the difference between the coordinates. So a Drinfeld center of the two category of T star Cn then would be endomorphic. So let's define it. So let me put here. I call it Drinfeld center, but what I mean by definition is category of endomorphisms of identity functor. So identity functor is an object in T star x cross T star x. Geometrically, it's T star x as diagonal in T star x cross T star x. I should say here, this corresponds to diagonal T star x. A Lagrangian subvariety in T star x bar cross T star x. So diagonal in the square, if you change the sign of one of symplectic forms, is Lagrangian. So this is what this correspondence is. So what is its home with itself? By definition, you get this lengthy matrix factorization category. So both sets of auxiliary variables, as well as variables x and x prime, and the superpotential, which is quadratic. So by Knorr, you can get rid of half of z's and half of x's. You can, in other words, change the variables so that z prime minus z and x prime minus x are new variables, let's say in addition to z and x. And then Knorr tells you that you can get rid of them. And so the answer will be matrix factorizations of 0 superpotential over essentially T star of X. So the center of the two categories is sheaves over T star of X. So the cotangent bundle shows up because of auxiliary variables that you need to describe identity functor. So the z's that you need to identify xi with xi prime, they in fact form a fiber cotangent spaces to x when you simplify the category of endomorphisms of identity functor.
Is the result any different if X is not T star of, if X is some general symplectic manifold, is that the same conclusion, or it's some different conclusion?
So a little bit later, I will explain what to do if it's not C star of Cn, but rather an open subvariety. So this is important case for us, and then the conclusion is the same. You again get, it's the same formulas would apply when you have open subvariety, and you would get the same conclusion. If you have a general symplectic variety, then it may be different. So again, the interesting case that we considered in our second paper with Kapustin is we considered a general case, and the difference between general case and this case is that this diagonal, of course it is Lagrangian, but its neighborhood is not exactly cotangent bundle to this Lagrangian. So again, in real symplectic geometry, a neighborhood of Lagrangian is symplectomorphic to cotangent bundle to this Lagrangian. It's Darboux coordinates. But in algebraic geometry, this is not the case. And so the neighborhood of diagonal is a deformation of cotangent bundle. And the leading deformation comes from a Tia class, which is a curvature of symplectic variety. So let me put it here as a side. Sorry, just a moment. So let me say it here. So now we consider a general symplectic variety as much as we can trust it. And then we consider diagonal, which is the same XM as XM, sitting inside this one cross itself. And the neighborhood of delta is not exactly cotangent bundle, and the first difference is described by a Tia class, which is curvature of the tangent bundle of symplectic variety. So it generates certain extension between, I forgot how to say it exactly, but this can be restored. So as a result of this, the Greenfield center will be still coherent sheaves over XSM, but the monoidal operation will be deformed. So it's still the tensor product, but with weird associativity. So we argue in the paper that instead of the usual associativity of tensor product, you get deformed associativity, and this deformation is again described by R, which was known before. It's or was it? Yeah, I think in Kapranov, Kontsevich, and one way or the other, in the Ginsburg papers, one way or the other, it's known that this guy deforms associativity of coherent sheaves over symplectic variety with the usual tensor product. And the way we argue is about this is we discuss what happens in general when you deform cotangent bundle, how this affects the construction that I was explaining. And the first deformation is given by what's known as second fundamental form, again, considered as a class. And this second fundamental form makes tensor product non-associative. We deform cotangent bundle to X by this class. And we consider endomorphisms of W equal to 0. What's the category of endomorphisms of 0 section? So before the deformation, that's coherent sheaves on X with the usual tensor product. After the deformation, it's still coherent sheaves, but tensor product is deformed and becomes non-commutative. And we have some formulas for this non-commutativity and strange associativity which comes with it. And then in those formulas, we set the leading deformation equal to 0. And what remains is the deformed associativity, exactly the one that we would expect from previous papers on the subject. So we get our weird associativity of sheaves over symplectic variety as the remnant of a bigger deformation. I'm sorry, maybe I should not have gone in these details because I didn't explain the basics there. But it is a funny story that maybe wasn't explored sufficiently. I'm sorry for this offside. So
it was super useful. Thank you. Thanks, Les. So thank you.
Thank you for listening to this. So there is a funny story. In fact, again, this whole story is categorified Kontsevich regarding formal quantization. So in this story, you quantize you quantize commutative tensor product. It becomes non-commutative and so on. So you compose functors again in the way of classical mechanics. Intermediate variety becomes all auxiliary. Now let me say a few words about Legendre transform. That's what you asked about last time. So suppose again our variety is Cn with coordinates x, and Legendre transform is Lagrangian correspondence which switches coordinates and momenta. So it is described by W, which is x times y. And you can check that if you compose this Legendre functor with itself, then you get almost identity. It switches the sign of symplectic form. So by composing functors and then using some Knorr periodicity argument, you will see that, well, sorry, not even Knorr periodicity. Here it's written. You go from coordinates x to coordinates y, and then from coordinates y to coordinates z. So you're supposed to add those functions. That's how you compose. That's how you compose correspondences. And what you see is auxiliary y multiplying x plus z. And you know that this is identity. So therefore, Legendre is equivalence because composing with itself gives you identity, except you switch the sign of coordinates. And explicitly, if you want to see why Legendre establishes equivalence between homes, between objects, here is a calculation. So you start with objects W1 and W2, simple objects, and consider category of morphisms between them. And then you apply Legendre. So now now you have auxiliary, X becomes auxiliary. So except I use prime instead of tilde. So X and X prime are auxiliary. And the final superpotential is the difference between Legendre transformed superpotentials. And then Bezout plus Cazul, you want to establish equivalence between these two matrix factorization categories. So you take the difference, you see that it is proportional to X minus X prime. And there is and there is the matrix factorization, Cazul matrix factorization, which establishes equivalence between them, specifically. So to finish maybe today, let me talk about the category of open subvariety. So this is an important subject because this allows us to introduce, to take account of stability in the definition of Nakajima varieties. So what if you want to limit yourself to an open subvariety of T star X? And I call it XSM. So the objects will be the same as in the old category, but homes will be different. So what's the geometric idea? Object is something growing over Lagrangian subvariety, and morphisms are coherent sheaves over the intersection. But now you want to exclude from this intersection, you want to exclude certain piece which you threw away from T star X. So formally, this is done the following way. If you have an object ZW, then you can map it. So you have a map from Z cross X straight into T star X. So first graph of DW sends it into cotangent bundle, and then you project along T star Z. So now you have a notion of stable part of auxiliary cross base. So you had, again, stab is I call it this way because it will be used for a stability condition. So don't read too much in this name. So originally we had some stability for T star X, which gave us XSM. And that was in T star X. But now we have a stable piece. We define a stable piece in auxiliary cross X itself. And that would be the preimage of stable piece in T star X under F, ZW. This formula.
If I'm a little bit confused by, so the very first line, you have X, one curl X, and another curl X. Is one like
I'm sorry, which line? I'm sorry, which line are you talking about?
Two category of open subvariety, and then there's a curl X and then another curl X.
Yes.
The first curl X is not a subset in the second curl X. It's subset in the cotangent bundle.
Yes, exactly. So I call it SM. It's symplectic. It's a symplectic variety.
Okay.
That's why I call it SM. So you see B2 star is of XSM, not of T star XSM. So XSM is already symplectic and it's not a cotangent bundle.
But we should think it's like open dense. Is it
open, just open?
Open. But like for example, there could be some Lagrangians in the cotangent bundle, they're just entirely missed by this guy?
Possibly. Again, the application will be to take the quiver definition of Nakajima varieties, and to, for example, a fine variety, a fine quiver which corresponds to instantons, and say that, say Hilbert scheme, say that vector with matrices X and Y have to generate everything.
So it's not exactly the same objects. Its objects are among the objects of the other categories. Not, there could be some Lagrangians which are just don't.
So the point, I will describe objects in the same way as auxiliary variety and a function on Z cross X.
Oh, okay.
So given an object of T star X, I can construct object of open subvariety of T star X.
Right, but for example,
it's trivial. Maybe it's trivial.
Could be an empty object, right?
Sorry. Yes. Could be.
Okay.
Yes.
Okay.
Sorry. So the point is that we can define stable part of auxiliary cross base. So in our description, we should not use momenta. The stability condition is formulated in terms of coordinates and momenta in T star X. So now we have to remove momenta somehow. So we remove them by keeping in mind that momenta are equal to partial derivatives of W. So that's what we use. So we take preimage of XSM in Z cross X. So in other words, we say that partial derivatives of W along coordinates of X should put us in allowed region in T star X. So now we have two options. Well, let's begin with one option. So to define morphisms, we have to take matrix factorizations over Z1 cross Z2 cross X. Auxiliary of the first, auxiliary of the second, and common coordinates, and take matrix factorization of the difference of potentials. So the stable part of the triple product is the intersection of stable parts. So we have two stability conditions for Z1X and for Z2X. We impose them both and define morphisms as matrix factorizations over the stable part of triple product. But a nice thing is that this category, I should draw an arrow here, this category, oops, sorry. Is equivalent to the category that you would get by imposing stability only on Z1 index. You can ignore the stability condition for Z2. And you would still get an equivalent matrix factorization category with a bigger base. And the reason is that the map F, which computes momenta conjugate to X, the Z1 and the Z2 map coincide on the critical locus of the difference of W's, because both maps are based on computing differential of W along X. So on the critical locus where both differentials are equal, these maps coincide. And matrix factorization category is supported in the formal neighborhood of critical locus. So one can argue that since these conditions are open, then in the formal neighborhood of critical locus, you could impose one or both, it doesn't make a difference. As a result, we have a functor from the unstable full T star X into B double dot of the subvariety. So the trick here is that composition of morphisms between Lagrangians will become composition of morphisms. The tricky part is that when you do the composition, you have to push forward over the intermediate auxiliary coordinates. And the result of push forward would depend generally whether you impose stability on Z2 or do not impose stability on Z2 index in the composition. Let me go back to the definition here. So the question is, if you want the composition of morphisms to agree in full T star X and in open subvariety, then there is a danger that when you do push back along pi 1, 3, you forget about Z2. The result will depend on whether you cut anything out from Z2 index. And good news is that the categories do not depend on whether you cut anything out or not. So you could do this composition with full Z2. So you could use the categories with full Z2, unrestricted. And that would be the same as with restricted Z2. So the compositions will correspond to each other. So therefore, we have a functor from the category of cotangent bundle to the category of restricted open subset. You do not change the composition because you cut anything from Z2, because the pieces that you cut are away from critical loci, or loci, what's the, away from them. So they do not affect the category of matrix factorizations. And this is good from technical point of view. So finally, and yeah, let me say about equivariant two category of cotangent bundle. So suppose there is a group which acts on X. So it has a Hamiltonian action on T star X. So the objects in the equivariant two category are auxiliary variety with the action of G, and a function which is invariant under the action of G on Z index. And this gives you Lagrangian fibration in T star X Hamiltonian reduction by G. And in fact, the Lagrangian subvariety will lie on the zero of mu in this construction. So there is no need to impose the condition that mu is equal to 0 in, for example, in computing morphisms, morally. So I'll just give a definition of morphisms. But Andrei's question of a week ago was, how does mu equal to 0 when you do Hamiltonian reduction affect the definition of morphisms? And the answer is, it does not. You don't have to account for it explicitly. Intuitively, because your Lagrangians completely lie within mu equals to 0. So you define, oh, where is the definition of morphisms? Oh, sorry. Just a moment, let me add one line. So home between object Z1, W1, and Z2, W2 now will be the category of G equivariant matrix factorizations over Z1 cross Z2 cross X of W2 minus W1. So on the face of it, at least, it's not bad. Okay, so Andrei, should I finish here, or do you want, so I have a little bit about derived algebraic geometry perspective, but maybe we could save it for whatever. I mean, if you want, I could talk for another 5 minutes or so about, or derived algebraic geometry perspective.
Sure. If there was something you were planning to say, just maybe you can say it briefly
And
now, then start again with it next time, so that there's some, more continuity.
Okay, so just to give you a taste, again, as I said, the story about two category of T star X is presumably equivalent to the story developed by derived algebraic geometers in relation to X, except they do not refer to symplectic geometry. So they work exclusively with X, and they see odd tangent bundle over X, but they do not see symplectic geometry. So that's why I think at least now our technical advantage is that we can handle open subvarieties. Maybe they have a way to handle them, at least for stability conditions somehow. So coherent sheaves over X form a monoidal category. So formally speaking, a module over the category, over a monoidal category, would be some category with functor from sheaves into category of endomorphisms of that category. That's just fancy words. And main example is the following. If you have a map from variety Y to variety X, then you can take a sheaf over sheaf E over X, pull it back to Y, and tensor with the sheaves of Y. And this makes sheaves over Y a module over sheaves over X. So now you want to define a two category of representations of coherent sheaves of X in this sense. So what should be morphisms between Y1 and Y2? So an object is Y with a map into X. Then sheaves over Y become modules over sheaves over X. What would be morphisms? Generally, functors from Y category of Y1 to category of Y2 would be coherent sheaves over the product. So you could pull back, tensor, and push forward onto Y2. But we want not all the functors, but the ones which are invariant with respect to the action of sheaves over X. So naturally, you would guess that as a morphism between Y1 and Y2, you would take coherent sheaves over the product of Y1 and Y2 over X. The trick is that you have to take this product in a properly derived way. So if Y1 and Y2 do not map nicely into X, for example, they do not cover the whole X or something else, fiber jumps, then you have to make sure that, I guess, this is properly derived. So a simple example, X is complex line with coordinate X, Y is skyscraper at the origin, so it's C of X mod X. So certainly it doesn't look free from previous experience. So you could use a resolution of this object of two category. Now, this must be a category. So your differential must be, so you introduce odd variable theta, and differential must be derivation with respect to theta, not multiplication, because you want a DG algebra. So what would be endomorphism of this category of endomorphisms of such an object Y? Well, you tensor multiply one DG algebra by another copy of itself over C of X. So you set X equals to 0 in the DG algebra, so differential goes away, X goes away, and you're left with modules over C of theta. So if you were computing X between skyscraper and itself, it would be C of theta. 0x and first X. If you compute their home as objects into category, then you get modules over C of theta. From symplectic perspective, the same story. Consider a special object, W equals to 0. Its endomorphisms are coherent sheaves with tensor product, a monoidal category. So now every object in our two category becomes a module, just for trivial reasons, over the endomorphisms of W equals to 0. So all our objects naturally are modules over sheaves over X with sheaves over X with tensor product. So we have a function from our two category into representations, presumably equivalence. So our object becomes now a module category, which is matrix factorizations of its W over Z cross X. Note that Z cross X is very nice with respect to X. It's free over X. C of Z cross X is free over X. So we do not need to worry about any derivation. So we have our matrix factorizations are free objects. Now, what about this skyscraper? You may guess that for subvarieties on the derived algebraic geometry story side, we have to take their conormal bundles. So instead of skyscraper, we take X equals to 0, its conormal bundle, so just X's moments equal of cotangent plane, cotangent line at X equals to 0. And this one is described by extra variable A and superpotential AX, as we discussed. And the morphisms of this object, by standard rules, would be, well, I should have written that explicitly. So that should be matrix factorizations of variable X and 2 copies of auxiliary variable, because now we have 2 copies of our object, of the difference of superpotentials. So we would get X times A2 minus A1. And now Knorr says that this is the same as matrix factorizations over just one variable A, let's say A1, and 0 superpotential, which means simply modules over C of A. Again, forgetting about degree. The very final comment, if you want to keep, you see in the derived story, the homological Z grading remained intact. Z. So if you want to keep Z on the symplectic story, despite using matrix factorizations, then you have to introduce the action of C star on cotangent fibers of T star X, acting with weight 2, and require that degree of superpotential should also be equal to 2. So superpotential should depend linearly on the fibers or on auxiliary variables if they also carry a weight of C star. So in this way, we could have a Z-graded 2 category, which would be equivalent to derived algebraic geometry. So yeah, so here I'll stop.
Super, thank you so much. How about questions? Come on, people. I've asked so many questions, so stupid ones too, and then, you know, you can ask some smart questions.
So I just want to say this is the end of general story. I'm sorry that it took so long. And so next time we'll talk specifically about quivers.
This Knorr periodicity result you talked about towards the beginning, is there some geometric way to think about it?
I'm sorry, could you say it again?
The Knorr periodicity results, is there a geometric way to understand this or think about it?
So usually it's applied to morphisms, and it is a particular case of saying that if your Lagrangian subvarieties intersect nicely, which means that at the points of intersection, their intersection looks like intersection of their tangent fibers, tangent planes. So either they coincide or they in every direction, either they coincide or intersect transversely. So they do not touch each other as parabola and x-axis, roughly. So if that happens, then the morphisms will be simply coherent sheaves over intersection.
Can I say a word? Can I say, add one sentence? So I'm
yes, you can always say anything you want in the seminar.
Okay, so maybe kind of less detailed way of saying it somehow, if you have a potential and you added some quadratic extra term to that, then the critical lossy wouldn't change if you add just quadratic term. So and basically like a magic factorization is all about the neighborhood or like some kind of neighborhood of the critical lossy of potential. But if you add to your potential quadratic term, then it doesn't change your critical lossy. That may be other way to say it.
That is almost true, except you can't really add like x squared.
You can, but then you have to. There's no.
Yeah, there's some kind of sign twist and so forth.
That's right. That's right.
Yeah, so if you add xy, then you're golden. Yeah.
Right. That's right.
Yeah.
Thanks.
I had a feeling that adding x squared to the story is a sort of shift from logical two category shift in a sense, but it never made sense of it completely.
Yeah, well, if you think about what x squared is, even not sure what it means, because xy could be x could be a section of any line bundle, and y is a section of the opposite line bundle, and they exactly just cancel. And whereas if you x squared is a section of some line bundle whose square is trivial, so that you know, that line bundle somehow comes into play. You have to somehow account for it. So that's anyway. More questions? Well, Lev worked really hard today. We thank him so much for this detailed explanation. Look forward to the next installment in a week. So thanks so much, everybody. We'll see everybody next week.
Thank you.